Yeah, okay, so our speaker is Göktuğ Karpat, Dr. Göktuğ Karpat from İzmir Economy University. And title of his talk is Synchronization and non-Markovianity in Open Quantum Systems. Okay, please go ahead.
Okay, thank you very much for the opportunity to present our work on the relation between synchronization and non-Markovianity in open quantum systems. Let me start by giving a very simple definition of synchronization. Well, we said that synchronization occurs between two or more systems that are independently evolving in time, start to evolve in unison or in coordination in time. In fact, this is a very old concept. It was first recognized by Huygens as an odd kind of sympathy between two pendulum clocks, which are coupled via a support. It's indeed, the synchronization is indeed a widespread phenomenon that we can observe in nature. Indeed, it's everywhere. I mean, I will just show some examples. For instance, I'm pretty sure everyone saw the example of a bunch of metronomes being coupled, when they're being synchronized when they're coupled through a common support. Or in the second picture here, you see a conductor imposing his own rhythm on the orchestra. These are different types of synchronizations, but well, let's clarify that as well. There are two different kinds of, we distinguish typically between two different kinds of synchronization. The first one being the spontaneous kind. So we say that the spontaneous synchronization occurs just due to the coupling between the subsystems in the absence of an external drive. So in the short clip here, you see fireflies flashing at the same time, more or less at the same time. They're synchronized. I think this is for mating purposes or something. There is no external drive, so this is an example of spontaneous synchronization. The second type is known as the forced synchronization, and it occurs when the system is actually driven by an external agent who, acting as a pacemaker and who imposes its own rhythm on the system. Here you see this guy who is actually imposing a rhythm on the other people who are rowing. Also, if you remember the conductor imposing his own rhythm on the orchestra, this is another example of forced synchronization. But in this talk, I'm just going to talk about spontaneous synchronization, actually. Okay, so, sorry. The synchronization phenomenon has been studied, relatively well in the classical domain, but in the last 10 years, we started to talk about quantum synchronization. So I want to clarify first what we mean by quantum synchronization. We say that usually, two quantum systems are synchronized when the local, the expectation values of the local observables of these two systems start to behave in a synchronous manner while they're undergoing open system dynamics, as they are evolving through the steady state. So it is a very simple example. Assume that you have two spin half objects labeled by S1 and S2. You can turn on an interaction between them as well, but the important point is that they are interacting with an external environment. Okay, so what we're looking at, what we should look at here to check whether the synchronization occurs or not is the expectation, the dynamics of the expectation values of the local observables. For concreteness, you can choose, for instance, the spin observable along the x direction, sigma x, S1 and S2. And well, what you want to do is you want to check whether, after a trend, of course, you assume some detuning between them initially so that the problem is not trivial. What you want to do is to check whether after a transient, period of incoherent oscillations, whether they become synchronized, anti-synchronized, or, frequency locked in some way. In the last 10 years, it was shown that both pairs of spins and oscillators show this environment-induced quantum synchronization behavior. It's a, rather timely subject, let's say. It was just, people started to study this like a decade ago, and there are not many works on it. Still, there are a lot of open questions. So this is one of the first works which introduced this concept. So for, just to give a physical model, I want to say a few things about this. Here, let's once again consider we have two spin half objects and they are coupled to a common environment through some interaction Hamiltonian, okay? And these spins have different characteristic frequencies, omega-1 and omega-2, so that there's initially, there is some detuning between them, because if there was no detuning, the problem would be trivial, right? So it was shown that the synchronization can occur between the local spin observables sigma x here once again. But at this point, I think I should say that synchronization does not depend actually on the choice of the observable. For concreteness, we choose some observable and display the plots. But I mean, for any spin observable, this should work, okay? So it's a characteristic of the dynamics, not the initial state, not the choice of the observable. Okay, in this model, they choose sigma x just to show the results. And as you can see here, the initial evolution in the green inset of these two expectation values show that there's no sign of synchronization here. They oscillate these expectation values. And then after some between 0 and 20, let's say, time, and after some period, there's a transient incoherent evolution. And finally, after some time, we can see that the anti-synchronization is achieved, and it remains as the system evolves, to its steady state and so on. So this is just this was one example. Of course, there are like several more examples for oscillators and spins. I just wanted to show you so that you have a feeling, about what we are talking about. But now let me start introducing our model and our results. So in our work, we considered a collision model for several reasons. But I mean, it's not important at this stage, but they are flexible. One of the reasons that we choose collision models is the fact that they're flexible. You can engineer any type of environment you like. This is one of the reasons. But what we do is that we study the establishment of synchronization between the local spin observables. Once again, the system, the principal system, which consists of two spins, S1 and S2, experiences open system dynamics as described by a two-qubit collision model. There is no external drive or anything, so this will be an example of spontaneous synchronization. So let me summarize the collision model, just the one step. So of course we are iterating this many times to reach the steady state of the problem. But in the first step, what we do is that we let the principal spin particles S1, principal system spin particles S1 and S2 interact directly with an XX type Heisenberg Hamiltonian. Here lambda is the interaction strength. In the second step, only S2 interacts with the first environment spin En with the same type of an Hamiltonian. In the third step, the S1 and S2, the principal spins, evolve with their free Hamiltonians, and at the same time, the environment spin En, which previously interacted with the spin S2, now interacts with the upcoming environment spin En+1. And in the final step, step 4, we trace out En and we continue with the same scheme with many, many more iterations. Here, maybe I should say that, that there are 2 points I want to clarify. The interaction between the environmental spins is described by a partial swap operator whose strength is characterized by this parameter gamma. So there are 2 parameters that are important for us: lambda, which is the spin-spin interaction, and gamma, which controls the strength of the intra-environment interactions. And as you can see, the first spin, S1 here, is like in some sense the probe spin here. It's not directly interacting with the environment, but I mean, it exchanges information with the environment over the spin S2, which actually directly interacts with it. Okay, so as you know, I mean, like you can guess from the title, I want to talk about the synchronization and the relation of synchronization and non-Markovianity. So I want to specify the measures because I want to talk about, this relation in a quantitative way. So I need to introduce the measures, right, for quantifying synchronization and non-Markovianity. First of all, to quantify the degree of synchronization between the spin observables, we use a standard tool from statistics known as the Pearson coefficient. And this coefficient basically measures the association between the discrete variables x and y. And in our problem, these parameters, these discrete parameters, will be the expectation values of the local spin observables sigma x s1 and sigma x s2. Once again, just to remind you, you can choose any other observable. Unless you choose something really pathological, you'll get the same result. Okay, so how do we calculate this Pearson coefficient? For two given data sets, if you calculate this, you get a number. But we want to see the evolution of this number, which gives us information about, the nature of synchronization. If Pearson coefficient goes to 1 in time, then it means that you have complete synchronization. If it goes to -1, it means you have complete anti-synchronization, for instance. So to be able to, look at its evolution, we do the following. Well, we first run the simulations and calculate the spin expectations after each step of the collision model, and then we group these. We divide this whole data set into smaller data sets, like in this example, data sets of 5 variables. We also allow some overlaps so that our plots will be like smoother. This is just for cosmetic reasons indeed. And then we calculate for each sub-data set the value of the Pearson coefficient, and we draw it as a function of the collision number. In other words, we could say it's time. Okay, so you see, we check either it goes to 1 or -1 or 0, I don't know, some other number. This will tell us about the nature of the synchronization. Okay, this is how we quantify synchronization, but what about the quantification of non-Markovianity? Well, this is rather straightforward. I will not spend a lot of time on this because this is now very well known. We quantify memory effects using the well-known trace distance measure. So we check the dynamics of the trace distance, taking arbitrary initial states, and then if there is a temporary increase throughout the dynamics in trace distance, we sum these increases. And since the increase of trace distance can be interpreted as a backflow of information, we assume that this quantifies memory effects or non-Markovianity. Optimization and the definition of the measure here for the collision model can be done numerically, obviously. But I should also emphasize at this point that our results do not depend on the choice of the non-Markovianity measure, because we have considered in our work also other measures such as correlation-based measures like entanglement, mutual information-based measures, and we pretty much get the same qualitative results. Okay, but another thing that I want to emphasize is we are just studying I mentioned that the first qubit is the probe qubit, which does not directly interact with the environment. So we are just calculating and considering the non-Markovianity of the probe qubit here. So this is the one that we will be comparing with the synchronization measure. Okay, so here is our main result, I would say. Let me try to explain this. In the upper 3 figures, you see as synchronization diagrams. They're color-coded. C12 is the Pearson coefficient, 1 and blue, correspondingly blue means full synchronization is achieved. Of course, this is the value of the Pearson coefficient after, say, like 10,000 iterations, so that the system reaches its steady state. And you see the blue means full synchronization, and the red means complete anti-synchronization between spin observables. And in the upper 3 figures, you see for the same parameter set, the non-Markovianity diagrams, color-coded again. The black means 0 non-Markovianity, and the yellow means the maximum amount of non-Markovianity. This is normalized. Okay, so let's first have, vertical axis is detuning or the ratio of the characteristic frequencies of the principal spins, and the horizontal axis, lambda, if you remember, quantifies the strength of the direct interaction between the spins, S1 and S2. If you have a look at the first two plots, the upper first and the lower first, you see gamma is set to 0. Gamma controls the strength of intra-environment interactions. Okay, this means that gamma 0 means that there is no intra-environmental interactions, so that the non-Markovianity, the only contribution to the memory effects comes from the direct interaction between the spin S1 and S2, because we're talking about the non-Markovianity of the dynamics of the first spin. So this is the simplest case. If you check this, you see that there's a line which sharply separates regions of synchronization and anti-synchronization, and along this line, synchronization cannot be achieved. Okay, and now for the same parameter set, if you have a look at the non-Markovianity diagram, you see that the greatest degree of non-Markovianity is achieved along the same line. So this was the first hint that told us maybe there's a trade-off relation between the onset of synchronization and the degree of memory effects. But of course, this is the simplest case. So to make this problem more involved, we next turn on the intra-environment interactions, like increasing the strength of gamma further and further. What you see here in the synchronization diagrams is that this line, this asynchronization line, let's say, shifts in the upward direction, but exactly the same behavior is, happening. You can observe the same behavior happening for the non-Markovianity plots. So our conclusion was there is indeed really a trade-off relation between the onset of synchronization and the degree of memory effects in the dynamics. So in other words, memory effects hinders the establishment of synchronization. I know that I don't have a lot of time left. I want to show you just last two plots. This is for the same data set, but maybe it's easier to see the trade-off from this plot. Now, along the vertical axis, we have detuning, and along the horizontal, we have the intra-environment interaction strength, which controls the degree of memory effects coming from the environment. You see again this white line, along which the synchronization cannot be established. And for the same parameter set, now if you check the non-Markovianity diagram, you see that the maximal value of non-Markovianity exactly corresponds to the same line. So indeed, there's a trade-off relation. But one might wonder, there is in this region, for instance, there is non-zero non-Markovianity, but synchronization or anti-synchronization is still established. Yes, it's true, but the next plot explains what happens there. Indeed, as the strength of the non-Markovianity increases, the establishment of synchronization is delayed. It occurs at a later time. So for instance, if you compare figures A and B, A is for piercing coefficient, so for synchronization, B quantifies the memory effects. You see, these are for different detunings. For instance, for the red line, we have the lowest amount of non-Markovianity, and the black corresponds to the highest amount. And in the synchronization plot, you see the black line reaches the value 1, the full synchronization, the last. So if there is more non-Markovianity in the dynamics, then the synchronization is reached, it becomes harder and harder to obtain the synchronized dynamics, let's say. So there's an inverse relation between two. Or to summarize everything, we can say, as the non-Markovianity increases in the dynamics, the establishment of synchronization is delayed further and further. And in some spatial region, it's so delayed that the synchronization can never happen. This corresponds to this white line here, followed by, this maximal non-Markovianity curve. Okay, so I think I'm almost out of time, so I will conclude by showing you the reference. And also, I want to say a few more things. Of course, due to the time constraint, I could not show all the results that we have in this paper. I mean, if you study the collision model, the results are numerical because you're doing numerical simulations, but we have also studied, I mean, master equation models in some simpler cases, because, you know, with the collision model, you can do anything you like, but if you use the master equations, if you want to obtain analytical results, you're more restricted. But at least in some particular cases, we were able to show that this relation can be, you know, shown to exist with analytical arguments. So if you are interested in the synchronization problem in the quantum domain, please feel free to also have a look at these two references, which are about the relation of quantum synchronization and quantum correlations and so on. Thank you very much for listening.
Thank you very much, Göktuğ, for this nice talk. So I think Francesco has a question. Please go ahead, Francesco.
Yes. Hi. I just had a small little curiosity. You stressed at some point that your results are independent on the non-Markovianity measure that you choose, and you mentioned quite a few of those. These are actually all measures that depend on the open dynamics of the system.
Yes.
But you know that you know, Kawamodi and others propose these measures, which also depends on the bulk dynamics. So I was curious to hear if something changes in these conclusions.
No, I understand. Okay, well, maybe I should correct. We just checked, you know, correlation-based measures and the trace distance measure. So I cannot, of course, claim that we have this. I mean, like we have the same trade-off for all the measures. That's something that I cannot claim, obviously.
And also, I wanted to ask you. Well, you've been playing, so to speak, with the collision models. I also play with that.
Yeah.
So a lot. Are these? You think these conclusions are model independent, or so?
Well, I mean,
if you go for more sophisticated models, you find similar.
That is not guaranteed, of course, but we have played with some master equations, of course, under some approximations, right? I mean, like some in the Lindblad form. Also, I mean, like in the weak coupling with the collision models, we. I mean, assume strong coupling, the results were the same. But of course, once again, I cannot claim if I complicate the model even more, which is easy to do with the collision models. I cannot guarantee that the same relation will be there. But it's not like a very specific instance. I mean, it's fake. I mean, I don't know, like reasonably general, let's say.
Right. Thank you.
You're welcome.
Thank you. Any other questions? So Göktuğ, what's the maximum dimension of the environment that you work on?
Here we are. This is a collision model, so we are just using spin-half qubits to model the environment. Like many qubits, but obviously, since this is a collision model, they are traced out after each, you know, iteration. So you have two-level systems interacting with two-level systems, but after each iteration, you trace out the environmental system. So I mean, like as you're doing the calculations, the full size of the system is never really very large. It's easy to do, I mean, numerically.
Okay. Okay.
I have a question. Can I ask?
Yeah.
Okay.
Please, yeah, go ahead.
You use the term non-Markovianity and the memory interchangeably, I think. Is it correct?
Well, it depends on how you define non-Markovianity and memory. It's correct to a certain degree. Well, what do you mean by I mean, it depends on what you mean by non-Markovianity. If you mean CP divisibility, and it's not equivalent to the BLP measure or correlation-based measures, but
my question is not this one, because if it is true, I mean, when you say the memory, you mean the memory shaped by these two principal systems, or the memory between the systems and the environment?
I mean the memory. I mean, okay. So non-Markovianity can come from two contributions here. First, since we are just talking about non-Markovianity of the dynamics of the first spin, the I mean, it can come from the direct interaction with the second spin. Even if the two spin dynamics is Markovian, there will be non-Markovianity in the single spin dynamics. Or it can also come from the environment if you allow the intra-environment interactions in the collision mode.
Okay, but I mean, intuitively, I expect proportional between the synchronization and the memory, because if there is a memory share between these two systems, then I expect a synchronization between their evolution.
I'm sorry, I couldn't understand the last part.
I said, I mean, if this memory, or let's say, I mean, this memory is shared between the systems, then
Yes.
I expect a synchronization between the evolution of these two systems, because there is a connection between the two systems by means of this memory. Then, I mean, if there is a memory shared between these two systems, then I expect they behave very synchronized.
No, not
Harmonizing.
understand, not like that. I mean, the second spin is still interacting with the environment, and it's undergoing decoherence. So the direct interaction does not guarantee synchronization. So without dissipation, there is no quantum synchronization. There must be dissipation. Okay, so although you have this direct interaction between spin 1 and spin 2, you must have some dissipation, because it's the key mechanism which enables the onset of synchronization.
Okay, thank you very much.
No problem.
Okay, thank you very much, Göktuğ, for this nice talk.
You're welcome.